everyone to TAMIDS workshop on reduced order modeling with pylibROM. This workshop is a result of the collaborative research between TAMIDS and Lawrence Livermore National Lab. I'm Suparno. I'm a postdoctoral scholar here at the Institute of Data Science. My area of expertise is in the computational modeling, primarily reduced order modeling.
Yeah. Hi everyone, I'm Pravija. Hi everyone, I'm Ragusa. I'm a master's in computer science student at Texas A&M University, and my area of expertise is in data analytics and developing software tools and applications.
So in this workshop, we will explore how pylibROM, the model reduction toolbox developed at Lawrence Livermore, can be utilized to efficiently reduce large-scale finite element models. We will guide you through. We will guide you from the basics of finite element analysis through advanced model reduction techniques such as proper orthogonal decomposition and dynamic mode decomposition. And we will apply these methods in pylibROM and demonstrate how to optimize and accelerate simulation of large-scale models. So for this workshop, we do expect that you have some background knowledge in introductory finite element analysis, linear algebra. You are somewhat familiar with dynamical systems. You are familiar with numerical solutions of ODE and PD, a little bit at least. And we assume that you have installed pylibROM Docker container. It was sent yesterday to an email. And we also would need you to install a software called ParaView. And we are going to send out a link shortly where you will be able to download the software for free and you'll be able to install it. So this is what is the structure of the workshop. So we have 4 sessions. In session 1, we are going to introduce reduced order modeling and pylibROM. And then in session 2, we are going to discuss how to set up pylibROM. And there we are, even though we sent out an email yesterday, we are going to again go through the native installation steps and or if you're using Docker, how to do that with Docker. And then in session 3, we're going to see pylibROM in action. We're going to talk about fundamentals of coding with pylibROM. And we are actually going to see an example of reduced order modeling. And then in session 4, we will discuss non-intrusive modeling of dynamical systems. Where so in this modeling approach, we will assume that we don't have any. We basically have data from a model, and without the knowledge of the model, how can we derive a surrogate model just from the data? And specifically, we are going to look into dynamic mode decomposition and how to do dynamic mode decomposition with pylibROM. Now, as a participant of this workshop, you have access to the Jupyter notebook files used throughout this workshop. You will have access to this PPT after the workshop as well. And you should be able to find the notebooks by clicking on this link that's appearing on the screen. So Pravija is also, Pravija has already shared the GitHub link in the chat. Can you please check if you're able to access it? hope you can see the same thing. So we have basically divided the folders based on the sessions, right? So, and you can actually use, so these are, though these are Jupyter notebooks, you also have the option to use the VS Code if you know how to run Docker container in VS Code. You can use VS Code, or you can directly use the Jupyter notebook. It's of your choice. And for some reason, if you are not able to run the Jupyter notebooks, for example, if you have had some technical difficulties installing Docker, just please follow along, and as we go through and explain each step. We also have participants. I just wanted to let you know that we also have participants from Lawrence Livermore on Zoom. If you have any questions regarding pylibROM or this workshop material in general, you can feel free to ask them the question, and we can also address any question that you may have. Please feel free to put them in the chat box. So let's get started with reduced order modeling. So large-scale systems such as turbulence modeling in fluid mechanics, or neutron diffusion and transport in nuclear engineering, reservoir simulation in petroleum engineering, and simulations in computational mechanics, for example, and biomechanics or structural dynamics. These are characteristically high-dimensional and or non-linear, and simulations of these systems require significant computational resources and may take an extended period, ranging from days to weeks to complete. So here is an example of an extremely large-scale problem. So this is the CFD simulation of a F-16 CD Block 40 jet, and the simulation is being done at a very high Reynolds number. This simulation uses 0.1 billion tetrahedral mesh elements, and like approximately 27 million vertices. Now at each vertex, we solve for at least 3 velocities, 1 pressure and temperature. So there's like 5 quantities per vertex, which leads to approximately 0.1 billion equations. And this high-dimensional model requires approximately 100.3 hours wall clock time on There we go. Okay, sorry for the interruption. So this high-dimensional model requires approximately 100 hours wall clock time on 3,584 cores on the front-era supercomputer at UT Austin for just 1.3 seconds of simulation time. Okay. You can see right away what kind of troubles we can get into. And reduced order model simplifies such complex systems by reducing the number of equations involved and approximates the behavior of a system with significantly fewer variables without compromising too much on the accuracy. And this reduces both the computational expenses and the storage requirements. Application of these models extend to embedded systems, robotic surgery, digital twins, and hypersonics. More generally, ROMs are useful for compute-intensive science and applications. For example, these are ideal for many query computations, such as design optimization, uncertainty management, optimal control, etc. Now, Intel, Boeing, Toyota, Ansys are some of the companies who regularly deal with extremely large-scale simulations for time-critical applications and often employ reduced order modeling. And many funding agencies such as DoD, DOE, NASA, NSF, they are also quite interested in heavily funding in this domain. So reduced order modeling strategies can largely be divided into two groups. One intrusive and the other one is non-intrusive. In the intrusive modeling, we require the governing equation in the form of and often in the form of a high fidelity model. And we may or may not need data depending on the kind of model reduction you want to do. So an example where governing equation and data both are used to form a reduced order model would be a projection-based reduced order model. And one feature of this intrusive reduced order modeling is that the reduced order model inherits the physics of the system, at least partially. And this intrusive reduced order modeling is what we are going to talk about in session 3. The other kind of reduced order modeling strategy is non-intrusive reduced order modeling, which is purely data driven. So you don't have access to the model, simulation model that generated the data, but from the data, you want to derive a surrogate model that approximately mimics the behavior of the system or generates similar data. An example would be Cookman operator or dynamic mode decomposition and deep learning based models such as neural ODEs, PDEs, neural operators. Here, the physics is not inherited by the surrogate model. So oftentimes you have to integrate the physics separately. An example would be physics informed neural networks. And in session 4, we are gonna look at one of these non-intrusive reduced order modeling strategies, which is DMD. So this is for session 3. Now again, within intrusive reduced order modeling, there are two classes of problems that we typically tackle. One is models formulated based on a system theoretic approach, and the other is models that are described with partial differential equations. So in models that are formulated based on a system theoretic approach, so here the models are described using large scale ODEs or DAs, and then the dynamics are characterized by a large scale vector. So this W is the state space for this large scale high dimensional model. And it's driven by inputs. And then we observe some outputs. And often the input and the outputs states are much smaller than the true state space dimension capital N. Now, the way reduced order models are obtained for this kind of models is that they're obtained by projecting the high dimensional model onto a subspace that discards state variables that are poorly coupled to the inputs or that barely contributes to the outputs. So states that do not get influenced by the inputs and the states that do not really contribute to the output, those states are discarded, and in that way we can compress the high dimensional model. These are not strictly data driven. You may use data or may not use data depending on the algorithm we use. Examples would be balanced truncation, moment methods, etc. The other kind of problem, the other kind of model is are those described using partial differential equations. So these are partial differential equations defined over a continuous domain that are discretized in space and time. Now, often these are discretized using either finite element, finite difference, or finite volume methods. And then we basically discretize these PDEs to obtain ordinary differential equations, which are pretty large scale. Because what happens is that the more you discretize, the more accurate your solution becomes. So there is an artificial dimensionality inflation that's happening here. And solution, unlike the previous ones, here we tend to seek after the solution over the entire domain. And this model reduction process requires data. So it requires both the governing equation and data generated by the high dimensional system. And the reduced subspace is derived based on a few high fidelity simulation data, such that, so basically in this case, we try to derive a reduced subspace based on the data generated by the high fidelity model. And this, we ensure that the subspace captures maximum variability of the data. And then the reduced order model is obtained by projecting this model, high dimensional model, onto this reduced subspace. And examples would be proper orthogonal decomposition, proper generalized decomposition, reduced basis methods, hyperreduction, etc. So for this presentation, we are mainly going to focus on these models, okay, PD-based models. And we will look into, so this is intrusive, and we are going to deal with models that are defined using PDs. And in session 3, we are going to look into projection-based reduced order model that uses the data as well as the governing equation. Any questions so far?
Yeah. For physics-informed machine learning, do we consider it as intrusive or non-intrusive?
Non-intrusive.
Okay. Because you still kind of solve the physical terms in the PD.
So the surrogate model doesn't inherit the physics by default. You have to integrate it separately. Say for example, in the loss function. Okay. So what's the basic idea is that we want to build the lowest dimensional model possible that can capture the dominant behaviors of the system by projecting a given high dimensional model on a subspace that is constructed after learning something about the data, something about the system of interest based on data or physics, whatever. So what is the fundamental idea behind model order reduction? Is that you leverage the lower dimensionality of the solution manifold. So what do I mean by that? Now, the intrinsic dimensionality of the solution of large-scale systems is often pretty low. As the solution resides in a lower dimensional space within a higher dimensional state space. So what we can do, we can leverage this phenomena and find a reduced order model with fewer dimensions, which can closely mimic the behavior of the complex large-scale system. So on the right, we have an example where you can see the solution of this dynamical system lies in this 2D submanifold in this 3D input space. And so even though if you didn't see the manifold, you would think that this is a 3D process, but when you can identify this manifold basically with 2 coordinates, you're able to express the dynamics instead of using 3 coordinates. So typically, there are multiple techniques for identifying the low dimensionality of an existing data set. What we are going to discuss is one of the most popular technique for data compression or data reduction. That's POD, or proper orthogonal decomposition. So here, given an ensemble of data, so what we are looking for? So say we have an ensemble of data, and we want to determine a basis set of orthogonal vectors which span this data optimally in the L2 sense. So say we have a data vector which is n dimensional, lies in R to the power n, and instead of finding a basis vector first, let's stick to finding a single unit vector, okay? And so we want to find out a single unit vector that yields the lowest one-dimensional representation error of the data in the L2 sense. So we have a multidimensional data. We are trying to find out a vector, and if we want to express the data along that vector, which we do not know yet, and we want that one-dimensional representation should have lowest error, because there are multiple possibilities, right? So we define an error E, which quantifies the discrepancy between the original data point Wi and its approximation Wi hat. We define this approximation as approximation Wi hat as the projection of Wi onto our chosen unit vector U. We do not know yet. We are trying to find this out. So the goal is to minimize this error E. Okay. So let's try to look at this picture. So here these purple dots represent Wi, and say we have chosen this horizontal line as our U vector. Okay. Now in that case, what is our Wi hat? So it's basically a vector from this origin. So let's consider this point. So what is Wi for this point? So this is the vector that joining from the center or the origin to that point, right? This is the original vector Wi, and Wi hat is the vector from this origin to this tiny orange dot. Okay. Now, what we want to do, we want to find out, and so what E here represents is basically the perpendicular distance between this line, this horizontal line, and this purple point, right? So basically E represents this distance for the ith point. Now we want to basically sum over all the points and calculate this total sum E. And then we basically want a direction such that E is minimized. So if we do, if we substitute Wi hat here and do some algebraic manipulation, we end up with this expression. But we find out that essentially, if we want to minimize E, we basically have to maximize this quantity on the left, because Wi is fixed. Okay. And so this is what? This is basically the projection length on this unit vector for these points, right? So for example, the distance between the origin and this orange dot is represented by Wi transpose U. It's a scalar, right? And we want to sum over all of that. So we now have a modified objective. Is instead of minimizing this quantity, we want to maximize this, right? And if we do some mathematical manipulation that, and we find out that this maximization problem leads to this eigenvalue problem, where Cu equals to lambda U. This is the eigenvalue problem, and C basically represents the covariance matrix of this data set. So if you look at here, the covariance matrix C is defined using this expression, and this W is a matrix that contains all these vectors as its columns. Okay. So essentially, if we can find out U, then we know the best one-dimensional representation for this 2D data. Okay. So as a matter of fact, if you solve the eigenvalue problem, so okay. Basically, what we're showing here is that we are trying to find out the best direction along which the variance is maximum or the projection length is maximum. But see, if you will notice that the moment this, I'm not able to fix it at this point, but the moment this this line aligns with U1, you will see that large orange dots that represents the first eigenvector actually of the covariance matrix C. So essentially, we started out with one vector, but in the end, we actually found out a set of basis vectors which are the eigenvectors of C. Now, these form a basis vector which we initially wanted to find out. Now, along with these basis vectors, we have our eigenvectors. We have these eigenvalues lambdas. Now, along the POMs, it can be shown that the variance is maximum, and this variance is given by these eigenvalues lambda. Okay. Now, the eigenvalues of C is a positive definite, so eigenvalues of C is greater than 0, and you can actually sort them from largest to smallest. Okay, and then now once we have these vectors and the corresponding eigenvalues, we can now use this information to find out our reduced subspace. Okay, so the question is how? So what we can do, once we have arranged our eigenvalues and eigenvectors in this way, then we can find out this quantity Rk, which indicates how much variance does these modes capture. Okay, so on the numerator we have a cumulative sum, on the denominator we have the total sum. So the quantity at the bottom represents the total variance of the data, and then on the top we have the cumulative sum, and we plot this. Here. So as you can see, as we increase the number of modes, it goes to 1. It ultimately goes very close to 1. So what we want to do is we want to include a certain number of modes such that the resulting subspace spanned by those modes capture a predefined variance of the data. Okay, so often we decide this epsilon tolerance number, so it's often close to 1, for example 0.99 or 0.9999. So, and we want to find out n, which is the dimension of a reduced subspace, which is the minimum value of k for which Rk reaches epsilon top. Okay, the minimum value of k for which Rk is Rk just crosses epsilon tolerance. Now, once we have n, we can form this this matrix containing the basis vectors u1 to u small n, and note this, check the size, capital N cross small n. And now we can project this data onto this reduced subspace and get an approximation u hat. Now, what is the error in this approximation? It can be shown that whatever variance you are not capturing, that's the reconstruction error. So if I choose epsilon to be 0.99, so if it's 99.9%, then you are not capturing 0.1% of the variance, and then that's basically the reconstruction error. Okay. Any questions so far? I think we covered a lot of material in 2 slides, but okay. So POD gives you another guarantee is that if you choose any other small n dimensional basis vector, set of basis vectors, the reconstruction error will be higher. So POD gives you the most optimal set of basis, n dimensional basis vectors for an n dimensional representation of the data. So far, for the last 3 slides, we have only talked about data compression. We haven't talked about model reduction yet. We had some data. I talked about how POD can be used to find a reduced subspace for projecting the for a low dimensional representation of the data. Typically, what we do, we use the same subspace for model reduction as well. So we have the system, we generate data, and then we find out the reduced subspace based on the data using POD, and then we project our high dimensional model onto this subspace. Now, I did talk about POD, but it turns out that we are mainly interested in finding out the left singular vector U. So it turns out that if you directly apply SVD on the data matrix, you can find out U. You don't actually have to calculate C and find out the eigenvectors and eigenvalues of C. You can directly do the SVD and you can find out U. However, the eigenvalues are not eigenvalues for POD are not same as singular values, and there is this relationship that relates the lambda POD with lambda SVD. Okay, as I was talking about, that we use, once we have identified the subspace, we assume that our approximate solution W to the of the high dimensional model can be expressed as a linear combination of the n dimensional basis vectors. So we write W as UN multiplied with W tilde. Now W tilde are the coefficients that we actually intend to find out. So we substitute this expression in our high fidelity model. Then and by Galerkin projection, we obtain this reduced order model. So we solve this reduced order model basically, which is n dimensional, small n dimensional. Often the small n is significantly smaller than capital N. So we have, after the Galerkin projection, we have a much smaller equation to solve. And once we have obtained this small n dimensional solution, then we can go back using this equation to obtain the solution in the full dimensional space. So as an example, if you have an LTI, but you already saw this example. So say you have this high dimensional equation where your W is R to the power n, and your A is capital N cross N, B is capital N cross P, M, and then so on. So these are pretty large. So what you can do, you can express your W in this way, and then you can substitute this in the LTI, and then we are going to get a much reduced system, which is basically from capital N cross N. You're going to boil down it to capital S small n cross N. So, and solving this equation is much simpler. Any questions?
Yeah, could you explain it one more time, because I couldn't get it? So U's are from the POD modes, right?
U's are from the POD
Yeah,
modes.
there are POD modes. W's are weights.
W's are weights
Or something like that.
linear combination. Right.
How do you find the weights?
That's the whole point.
Okay, you're
That's
trying
what
to find a way.
That's what we're trying to
Okay.
find. W tilde, so this whole equation is in terms of W tilde. In terms of, but this is much reduced, only small n dimensional. And once you have solved this, then you can use this equation to go back to your full dimensional space. Okay. Okay, so there are multiple model reduction tools available. This list is by no means exhaustive. So we have libROM that's developed in Lawrence Livermore. We have PyMore and More Lab that was developed in Max Planck. We have Slycott, MATLAB, IDMD, which was developed in Sisa, Italy. Out of all these tools, today we are going to focus on libROM, developed at Lawrence Livermore. These are the contributors. And let's get familiar with what pylibROM is. So libROM is basically a software library for reduced order modeling and more generally for data-driven physical simulation methods. It's written in C++ and it's designed to be lightweight, portable, and scalable. And we have and the library is open source, available on GitHub. libROM webpage, you can see the snapshot here. It hosts a lot of examples, and there are tutorial videos on YouTube. There are different features that are already documented. Now, pylibROM is basically a Python wrapper around the libROM library. And pylibROM builds upon the PyMFM finite element package, which was also developed in Lawrence Livermore. And like pylibROM, PyMFM is a Python wrapper for the original MFM finite element package, which is also based on C++. So we have libROM, pylibROM, and we have MFM and PyMFM. Now, if you want to install pylibROM, you have to ensure that all four things are installed on your system. Now, as you know, reduced order model is a very active field of research, and the libROM community is committed to developing state-of-the-art algorithms. With pylibROM, we can do both intrusive and non-intrusive reduced order modeling. And this slide showcases the intrusive model reduction capabilities of pylibROM. pylibROM not only hosts the traditional model reduction strategies such as pROMs or projection-based ROMs, but also innovates on new model reduction techniques such as nonlinear manifold reduced order modeling, space-time reduced order models, component-wise reduced order models, etc. And as a result, pylibROM is capable of solving a wide range of problems, starting from Lagrangian hydrodynamics problems, particle transport, to design optimization. This slide shows the non-intrusive model order reduction capabilities of pylibROM. The examples shown here are based on DMD, which we will discuss in the last session. And this is one of the leading non-intrusive modeling approaches. For computationally demanding applications, DMD can be very beneficial. One such application is the additive manufacturing. So this is an ALE 3D simulation of laser tracing, which takes about an hour to complete. So basically, what ALE 3D is, it stands for arbitrary Lagrangian Eulerian 3D analysis. It's a versatile multiphysics tool, also developed at Lawrence Livermore. But it gives high fidelity simulation, but it takes a lot of time. So, however, if you implement DMD, you can attain just with 0.1% of maximum relative error, you can achieve 50,000 speed up. That's pretty huge. And you can also tune the trade-off between accuracy and the speed up using DMD. Another application stopped. Another application is the port collapse simulation by ALE3D, which takes up to 1 week on 1,000 cores to finish at each applied shock pressure. With DMD, this simulation can be reduced within 1 minute on a single core with only 0.3% relative error. Yeah. So now let's move on to session 2, and Pravija is gonna talk about how to set up pylibROM.
So, are you able to hear me? So in this session, we are going to discuss how to set up pylibROM on our systems. So there are two approaches. One is native installation. The approach one is only compatible with Ubuntu. For now, pylibROM is only compatible with Ubuntu. So users who have Ubuntu can follow the approach one. And users who doesn't have Ubuntu, don't worry, we are going to show how to install pylibROM in different way in approach 2. So in order to install pylibROM, we need to have all the dependencies. We need C or C++ development tools such as Make, GCC, G4tron, and CMake, and Python dependencies such as NumPy, SciPy, RParse, tables, etc. And in addition to this, we also need Swig and PyMFM libraries. So you can install all these tools and dependencies by using these 3 commands. And yeah, after this, the next step is to clone the pylibROM repository. Once you have successfully installed all the dependencies, the next step is to clone the pylibROM repository. And once you have cloned the pylibROM repository, you need to compile and build it by using the command pip install. And make sure that you are inside the path of inside the pylibROM folder before compiling and building pylibROM. And after this, if you have used libROM previously and if you have already compiled it in your system, you can speed up the build process by using this command pip install global option and this command. So for the users who doesn't have Ubuntu operating system, you can follow the approach 2, and users who also have Ubuntu can also follow this approach. It's up to you. So yeah, using Docker container in this approach, in order to install pylibROM, we are going to use Docker. So make sure you have Docker on your system. So for people who are unfamiliar with Docker, Docker is nothing but it's a platform where it provides us a platform where you can combine all the dependencies and our application into a single package. So, and you can run the application inside the container, which provides us all the dependencies that are required to run our application. So installing Docker, you can follow this link. In order to install Docker, we have provided here. For Linux and Ubuntu, you can provide this link. It's available in the official Docker documentation. And for Windows and Mac OS, you can use Docker Desktop. We'll share these links. Don't worry, we'll share these links at the end of the workshop.
We'll basically share the entire.
Yeah, we'll
PPT.
basically share the entire PPT. So, and even if you're not able to install pylibROM for now, don't worry, we can have a session after the workshop where we can address your issues. So yeah, pylibROM using Docker. So once you have installed Docker, now you need to clone the pylibROM into your local system. And once you have cloned, you can pull the Docker image that's available here. And after you have successfully pull the image. Once the image is built on your desktop, you can run the container, you can create the container and run it by using this command. And make sure that you give path to the folder of pylibROM. Replace this path with your path to the pylibROM folder. And once that's done, once you have successfully created the container and run the container, now you will be inside the container and you need to build and compile the pylibROM. So in order to do that, you can use this command. So this is the installation process for pylibROM inside Docker container. For users who are more comfortable with Jupyter Notebook, and if you want to access pylibROM inside the Jupyter Notebook, we have another Docker image which provides us access to pylibROM library inside the Jupyter Notebook. So in order to use pylibROM in Jupyter Notebook, you just need to pull this image, and once you have pulled this image, and then you need to run the container with this port. So once you have run the container, then you'll get a link with this port number. So you just need to click on that link, and then you'll be able to access the pylibROM in Jupyter Notebook environment. Yeah, that's good. Any doubts?
So we'll resume after 10
Yeah.
minutes.
He's the last option. He's the last option.
No, it's not like. When I ask my students to do that.
So in session 3, in part 1, we are going to see the basic functionalities of pylibROM. So I already have pulled the Docker image, so I'm just going to run the container.
Are you able to zoom in, make the fonts bigger, make it hard to see? It's Control Plus, I believe. Yeah.
So I have replaced the path with my relative path, the path where I have all the workshop material. So if you also want to run the codes, and if you also want to run the examples that we are going to show in later sessions, make sure you also replace this path with the part of the workshop material. So this gave me the link. So I'm going to click on it. So yeah, pylibROM provides these functionalities. It provides various kind of algorithms such as related to data compression. It provides different types of SVDs, singular value decomposition techniques. You can, if you are interested and if you are willing to learn, you can go through the pylibROM repository website and there you can access these algorithms. And you can also, if you want to learn more about the algorithms and what's going internally, you can go through the libROM documentation page where it explains about these algorithms. And it also provides different types of hyperreduction techniques such as DIME, GNAT, SOPT, EQP. And in non-intrusive methods, it provides various variations of DMD. It provides non-adaptive DMD, parametric DMD, and simple DMD. So in session 4, we are going to discuss about the simple DMD and we will explain it through an example. And it also provides different type of parametric reduced order modeling techniques such as 3D algorithm and matrix interpolation. In this workshop, we are going to discuss only about PROM and DMD. So yeah, pylibROM also provides linear algebra module in which it provides all the essential linear algebra functionalities that required for reduced order modeling. So it provides various classes such as vector, matrix, SVD, basis generator, basis writer, basis reader, and NNLS. Vector, the class provides all the functions and operations related to vector manipulation, and matrix, it also offers operations and functions related to matrices. And in singular value decomposition, it provides algorithms for matrix factorization used in dimensional T reduction and data compression. And basis generator, basis writer, and basis reader, these classes and these objects are used to create snapshot files. Basis generator is used to create basis snapshots, and basis writer, it writes the basis snapshots to basis file. And basis reader, it is used to read the basis snapshots from the file. So here we are going to discuss about vector, matrix, and SVD because these are some of the basic and important components, because most of the algorithms that's provided by the reduced order models, it takes vector and matrix as the inputs, as parameters. So yeah, in order to create a vector object, first you need to import pylibROM.linear algebra module because vector class is available in linear algebra module. And then if you want to do if you want to create NumPy objects or anything sort of, then import NumPy or any other libraries. And now, in order to create a vector object, we just need to run this command linear algebra.vector, and inside that we need to, the first parameter says the size of the vector. We need to give the size of the vector here, and distributed, this parameter says whether we want to run distribute our vector in if you want to run our algorithms in parallel environment, and if you want to distribute, if there is a large vector, then if you want to do computations on multiple processes, then we need to set it as true. But for now, as we are using only one processor, I'm setting it to false. And d.fill, this function basically sets the each value of the vector with 1.0, the value that we give inside the function. And in order to get the value of get the data of the vector, we need to use the command v.getData, which gets the data of the vector, as shown here. So yeah, you can even create a vector with NumPy array. I mean, if you don't want to give the size, or if you don't know the size of the vector or something, and if you want to give some NumPy array as an input, then you can give it in this way. You just need to give inside the vector the parameter as array, the NumPy array, and then you need to set the distributed parameter as false or true based upon your requirements, and that's it. And if you want to resize the vector after initially if you have set the size to 3, and if you want to resize the vector, then you can use this set size function which resizes the vector to 3. And the set item, this function sets the particular column or particular item of the vector. If you want to change the value of the second index of the vector, then it changes only that particular, it sets the only particular item to that particular value that we give inside this set item function. Here the first parameter is the index and the second parameter is the value that we want to give. And if you want to get item of only particular index, or if you want to get particular index value, then we need to use get item, which gives us the value. Here we want the value of index 1. So here it gave us the value of index 1 as 2. So if we want to add two vectors, then the addition operator adds the vector b with vector w and it stores the value into vector v. And not only this, it also provides subtraction and it also provides different types of multiplication and other functionalities. If you want to use those functionalities, go to the pylibROM repository. There will be a vector class and you can see all the functionalities that are provided by the vector. So v dot normalize, this normalizes the vector, and v dot inner product is used to do the inner product of v with w, and it stores this product in inner product. And if you want to do scalar multiplication of vector, then you can use this function. And if you want to do if you want to multiply one vector with another vector, you just need to, in place of 2.0, you just need to give v1, v dot multiplication of v1. Yeah, that's about vector class. Not only this, it provides many other functionalities. So go and check out the pylibROM repository. In matrix, similar to vector, you also need to import the linear algebra module if you want to create and access the matrix objects. So you can create a matrix object by using the command linear algebra.matrix, where the first parameter says the number of rows that we want to create the matrix with, and the second parameter is about the number of columns that we want to create the matrix with, and the third column is distributed, whether we want to run it in parallel environment or not, and whether the fourth parameter says whether the distribution is randomized or whether it is uniform. So the m1.fill, this function also fills the every value of the matrix with 2.0, and m1.getData, it gets the data of the matrix. So as we can see, we have set each element of the matrix with 2.0, and then each element is 2.0. So if we want to get the number of rows in the matrix, then we need to use the command function m1.number of rows. And if you want to get the number of columns in matrix, then we need to use the function m1.number of columns. So if you want to create a matrix with NumPy object, similar to vector object, here also we need to create a NumPy array object, and then we need to give it to matrix, and the second and third parameters are distributed and randomized. And if you want to resize the matrix similar to vectors, here also we'll be using the set size function, which resizes the matrix with different columns and rows that we are going to give here. And set item and get item, it sets particular value of the initially all the elements are 3.0. Now if you want to set particular item, particular row and particular column element to some value, then this function sets that particular row and particular column with the value that we give here. And if you want to get the item, get particular element, then we need to, this is the first parameter is the row, and the second parameter is the column. And yeah, if we want to get the entire column or entire row, then we can use this command m dot matrix dot get column of 1, which gives us the first column. We are here, the matrix and vector classes follow zero-based indexing. So m dot get column of 1, it gives us second column of matrix. And if you want to multiply one matrix with another, then we need to use this function which multiplies m2 with m1. And if we want like outer product of two vectors, and if you want to store it in a matrix, then there is the outer product functionalities which takes the vectors v and w and gives and stores the output and the result matrix in the variable. Yeah, and here is the output, the outer product of these two vectors. And if you want to do inverse of the matrix, then we can just simply call this function m dot inverse, which gives us the inverse of the matrix. And if you want to get the transpose of the matrix, then we can use the function m dot transpose, which creates the transpose of the matrix and stores it within the matrix itself. It changes that matrix to the transpose matrix. Yeah, if you want to do orthogonalization, then m dot orthogonalize function, it orthogonalizes this matrix. And if you want to get the diagonal matrix, then we can use this command. And similar to that, if you want to get identity matrix, then we can use this command. Yeah. And that's it about the matrix class. There are other operations as well. And SVD, like I said earlier, pylibROM provides different variations of singular value decomposition, especially for reduced order modeling, such as static SVD, incremental SVD, and randomized SVD. But this is the basic SVD that's provided by, it's similar to the one that's provided by NumPy and other libraries. So we just need to create a matrix, and then we just need to call serial SVD of M, which does the singular value decomposition on this matrix, and the result is stored in the serial SVD object, and we can get U, S, and V, U, S, and V with the help of this by doing this serial SVD dot U dot get data, which gives us the data of the singular value. Yeah. These are some of the basic functionalities, and we have explained this because most of the algorithms and examples that we are going to demonstrate in this workshop takes this the vector and matrix and SVD objects as parameters. So yeah, if you are interested in learning more about the linear algebra module that provided by pylibROM, go to the pylibROM repository, and there you can click on bindings, and inside that there will be a pylibROM folder. Inside that there will be a linear algebra module, and inside that there will be all these classes. Yeah. Now Suparno is going to explain one of the example of pylibROM.
Okay, any question regarding this? This is open, as she was saying, this is an open source repository. You can go to the website and check out any function in detail. So I'll stop sharing the screen for a second. So let's actually look at one example where we perform reduced order modeling. Basically, we are going to look into projection-based reduced order models as we have discussed before. So, as a representative example, we will consider this parametric 3D, which is a steady-state linear heat conduction solution. It's defined over some domain omega. So here K is the thermal conductivity and Q is the local heat flux density. So Q is a function of X and mu. Mu is the parameter. So basically, we want to perform this. So this being a parametric PD, what we want to perform this calculation. We want to solve this PD for different values of mu. What happens is that, as you will see, we are going to use, first we are going to use finite element method to develop a high dimensional or high fidelity model. What typically happens is that when you have a high fidelity model and if you want to evaluate for multiple parameters, it's going to be slow. So that's why we basically need a reduced order model for this kind of problem. So these are possible boundary conditions for this PDE, and the Dirichlet, Neumann, or Robin boundary condition. So I'm gonna briefly go over some of the steps that we need to do in order to develop a finite element model. This is definitely not a finite element lecture, so I'm not going to go in detail, but some basic steps I will cover here. So we start with the weak form of the heat conduction equation. Weak formulations are at the heart of finite element method. In finite element approximations are almost always less smooth than the solutions we hope to approximate. So basically, if we want to estimate the actual solution that we typically cannot do, and we approximate with finite element, and it's almost always less smoother. And this lower smoothness of the finite element approximations require integrating the governing equation over the entire domain instead of solving them at individual points within the domain omega. And so this integral formulation is derived by multiplying the PDE with a test function Px, which vanishes on the boundary, and integrating the result, we get this expression. And so in order to go from second step to the third step, we use this vector identity and the divergence theorem. Now, this is basically the weak form of the strong form of the PDE. And this is called a bilinear form. Okay, this is what eventually leads to a stiffness matrix. And on the right hand side, we have the linear form. This forms the right hand side vector. Just remember these two jargons, like bilinear form and linear form. We're going to use them in MFACs. So here also, as you can see, we get a boundary term, and depending on the boundary conditions, you're going to replace this term based on the boundary conditions you have for your PD. But here, like for our problem, we will basically consider this to be zero, because we will be considering Dirichlet boundary condition where this test function is zero. Okay. So the finite element method is based on the notion that the solution Tx can be approximated by a sum of piecewise smooth functions, which are typically piecewise polynomials called basis functions or shape functions. The support and by support I mean like this region where this function is non-zero, will either be a single zone. For example, if we consider this shape function, so this is defined over this zone, or over a collection of zones that share a common vertex or face or edge. The number of basis functions, how many, so what your n will be, is dependent on how you discretize your domain, as you can see here, and how many mesh elements you have. And so these expansion coefficients Ti, they are also often called degrees of freedom. So essentially with the finite element method, we find out these DOFs, and here we have this T vector which contains the DOFs. So we substitute this expression of the solution T into this weak form, and we write this weak form as a sum over different elements, and which leads to this large algebraic equation. So you have K times T vector is equals to Q. So K is n cross n, T is n plus 1, and Q vector, which is the source vector on the right hand, which comes from the source vector on the right hand side. So this is pretty high dimensional, and it like the larger n is, the larger this system is. If it's huge, then solving this is going to be difficult, at least iteratively for different parameter values. So what we are going to do is that, as I told you, our objective is to find out or do this calculation for different parameter values and find out the solution for different parameter values. So what we are going to first do, as I told you before, in projection-based reduced order modeling, what we do, we take a parameter, get the solution, and we stack it into this data matrix. So we find out the solution for mu1, mu2, and stack as a column vector, right? And then we want to do POD on this, but we don't need to do POD explicitly. We can just do SPD because we are interested in finding out the left singular vector u. And based on the truncation method that I described earlier, we can just select small n columns from u, okay, to formulate this u tilde. Okay. So on the right hand side, I just compare the shape functions with the types of functions we get in SVD. In both cases, we assume that our solution is a linear combination of these basis functions. But here, as you can see, this POMs basically represents proper orthogonal modes, which is another name for these singular vectors, are defined over the entire domain. However, the finite elements are defined are supported locally. Okay. So is this just for visualization? So how do we build the reduced order model? So we have u tilde, and as I think I mentioned briefly before, that you assume that your solution lies in the subspace defined by the column vectors of u tilde. So you write it like that, and then you substitute this in this equation, right? And you obtain this reduced equation. We have u tilde transpose k u tilde. So now this yields a small n cross small n stiffness matrix, denoted here as k small n. And then you have Tn. Again, this is a reduced vector. And you project Q onto the subspace, and you get Q small n. Now this reduced system is much easier to solve, right? You can just maybe do a K inverse Q and you get Tn. This inverse can be done very easily because it's much smaller. And then once you have Tn, T small n, then you can go back to your original full scale T just by multiplying with T. So let me summarize the whole process. Are you guys able to read this? Person in the back, not really there.
But we can say it in Zoom.
Oh. Okay. So we have a parametric PDE, which was the heat conduction equation. Then we employed finite element method to. This is not for our case. It's not ODE. It's a bit simpler. We just have algebraic equation. It's a large scale algebraic equation. And then these are high fidelity models, and we solve for different mu values. Okay. Then we ensemble this solution. Then we generate an ensemble of solution snapshots, and then we do proper orthogonal decomposition or singular value decomposition, and we get the reduced basis. Then we take this large scale ODE, and then we do a Galerkin projection, and we get a reduced order model. Then we now use the reduced order model to get with a new parameter value, and we get a reduced solution. And then using the reduced basis, we lift the reduced solution onto the full order space, and we obtain the solution. Now this track is much faster than if we were to follow this track for achieving this solution for this new parameter value. Okay, any questions here?
So you're not using the governing equations after you make the reduced model in this case.
So we make the reduced order by using the high fidelity, by projecting the high fidelity model onto the reduced subspace, and this high fidelity model was obtained from the governing equation itself. We do not use it directly, but indirectly.
So my question is, if the mu nu is, let's say, beyond what we used to make the small scale model, right? How good is it going to?
It's not good.
But
So
if you have the governing,
extrapolation is typically not that great.
But if
It
you have
all
the-
depends on the problem.
yeah, but if you have the information from the governing equation, right? Even though you are extrapolating, it should get some information out of the governing equation.
It's not gonna be too off, it's gonna be off, but the thing is, it depends, because if you have a parameter too far from your training parameters, then the reduced subspace is probably not correct. So you are assuming that the solution will be contained in that subspace, and that's why you are using that reduced order model for a different parameter value. Assuming that the result for the new parameter value will still lie in that reduced subspace. But that may not be the case if the parameter is too far away from the training parameter. Okay, so now let's look at a very specific problem. So here we are gonna look at the heat conduction problem where we have. So we have this domain, star-shaped domain, okay, and at the boundary, it's basically a homogeneous boundary condition. So at the boundary, the temperature is 0, and the flux density is Q, and it's a function of kappa. So here the parameter symbol is different. Instead of mu, I have kappa, and it's a sinusoidal function. And we will basically train, we will generate snapshots with some training parameters and formulate a reduced order model and see how that model performs when we use new parameter values basically. And we are going to see how to do this in pylibROM. Okay. So again, going to the screen a little bit. I apologize. The Zoom participants. So I would urge everyone to open the session 3 part 2. Notebook. If possible. So, anybody having any difficulty opening it? Yes.
I'm in the folder, but it's not allowing me to open
Allow you to open.
the Jupyter now. Permission denied. Yeah.
I'll just start.
The workshop folder is available in the Zoom chat. Could you open it?
Okay, so basically I have the same figure that I showed before here. But I just wanted to say, lay out basically how this whole reduced order modeling is performed in pylibROM. So there are 3 stages. So we have an offline training phase, we have a merge phase, and we have an online phase. So in the offline training phase, we basically generate the snapshots for different parameter values. In the merge phase, we ensemble the solution snapshots to SVD and generate the reduced basis and perform the Lurkin projection. And in the online phase, we perform the reduced order modeling and for a different and obtain reduced solution for new parameter values. So we can. So these are the 3 distinct phases. So this file is like a master file. It does. It basically incorporates all these 3 stages and evaluates the performance of the reduced order models that are generated using pylibROM method. But before doing this, let me go inside the individual files and give you some idea of what's going on inside.
Yeah.
So this data generation corresponds to this data generation corresponds to this offline training phase. Okay. Now this is where all the finite element simulations are being done. So these are some regular imports of packages from MFM. Now by construct, MFM and pylibROM. By construct, pylibROM is capable of handling parallel computation. Now we can either do it serially or in parallel. There are 2 ways of doing it, but here we are showing how you can do it in parallel because it still works when you do not have multiple cores. If you have a single core, it will still work. If you want to do it serially, you instead of importing mfm.per, you can import mfm.ser. Okay. There is another way of doing it, but here we will mainly focus on a parallel execution. So the first thing, let's see, let's go through the steps. So here we initialize a parallel environment. Then in get parser, we basically incorporate certain arguments. I'll quickly open what the first one is. So here you have different options that you can specify. For example, you can specify the mesh file, the order of the finite element. For example, what is the order of the finite element? Is it first order, second order? If you specify -1 size parametric in that way. Then this is the ID, like ID of the simulation. If you're iteratively generating multiple solutions, then you have to have different IDs. Then NS is the total number of snapshots. I think you remember capital NS, how many training parameters you are going to use. Then this is static condensation, not that relevant here. So here frequency, this frequency parameter basically is equivalent to kappa. Then this coefficient, not so these are visualization options. Now we have three options. This is important. So we have FOM offline, online, and merge. So as I told you, you have to select when you are generating the offline simulation data, you have to opt for offline. If you're generating online, like when you're generating for new parameter value, you have to select online. And during the merge phase, where you're generating reduced weights and reduced total model, then you have to choose the merge phase. Okay, and this paraview is just for visualization. So there are multiple visualization options here. So you have paraview, you have visit, and then there are others that you can go through online. You can see there are other options, GLBase, etc., available as well. So we basically set the options here, and we call it from this data generation file. Remember, this is the file which generates the offline data. Now we select some parameter value, and this is phase one because this is basically training, generating training data. And we, from based on whatever we choose in the parser config, we basically extract those values and store it in those variables. So then we specify how many maximum number of snapshots we are going to train with, and these are some basic bookkeeping where you are going to store the data, etc. And M-term device, if you have GPU, you're going to probably get GPU, and otherwise the default is CPU. And now this is the mesh, the star-shaped mesh, and this is like a zoomed in view of how the mesh looks like. And we are going to load the mesh file that's already available here. Okay. Using m-pem.mesh. And this is a two-dimensional mesh, so we store that in DIM, and then we refine it as many times as we want. So there is a limit set here. It should not go more than 10,000 elements. In the file will no more than 10,000 elements, right? And then once we have read the mesh file, now we generate something called pmesh. So this is a parallel mesh. So we take the mesh, and now we can distribute that mesh among different processors, and that can be done very easily here. We just using this command. And once that's done, we clear the serial mesh. Now, This, so now we, in this command, we define the elements that we are gonna use. So we have the mesh elements and then we have defined the mesh and then we specify the finite elements that we are gonna use. And we, once that's defined, we generate an FE space. Okay, so it's a power finite element space. Where we input the parallel mesh and the elements that we use to generate the stiffness matrices, for example, and basically do the finite element formulation. So we put that inside and generate this FE space object. When we check the size using FE space global true B size, it gives us the total number of unknowns that we have to solve for. Here, now out of those unknowns, some of the nodes correspond to the boundary, right? And we already have a Dirichlet boundary condition applied. So we have to identify on which nodes we have 0 value because those are on the boundary. That's what this step does. And then we define the right hand side, the capital Q, the small q. So this is basically the right hand side Q. Okay. Okay. And then we assemble. So this add domain integrator, so this domain LF integrator F. So this, what this does is basically for every element, it is going to calculate, it is going to do this particular operation. Okay. Over every element, it's gonna generate, evaluate this integral for every element. And whenever you assemble, you're gonna sum it up and generate this integral. Okay. Then you have, so X is where the solution is the object that will contain the solution. So this has both the Dirichlet conditions and the Dirichlet values as well as the values inside the domain. So it contains both. And as I told you that this bilinear form, as I showed here, so this M-fan bilinear form is constructed based on the FE space we have defined. So basically A again does something very similar to this B domain integrator. So from A, we are able to generate this stiffness matrix. Once we have, once we run this add domain integrator, it's gonna do this integration. And when we do assemble, it's gonna assemble it and generate this large stiffness matrix. Now, we are not gonna solve for the boundary elements because boundary nodes, we already have 0 values on the boundary. So what we are gonna do, we're gonna create this form linear, we're gonna invoke this command, and we're gonna pass on which boundary nodes has Dirichlet boundary condition. So we're gonna pass that X, B, and we have A here. So this line will basically generate this equation. Okay, so it's gonna generate Ax equal to B. And then typically, when the system is this big, you don't just do an inverse. You use other techniques to basically solve this. Here we are going to use conjugate gradient method, conjugate gradient solver. We are going to define a CG solver here. We are going to set the tolerance, maximum iteration. And then at this step, we are going to solve for t, in this case denoted using x, and that's it. So we are going to generate that as x, and remember that we have distributed the mesh over multiple elements, so the calculation is happening over multiple elements, and this recovered solution basically gathers everything and put that in x, small x, and then we store that data and save this data for visualization and in development. Okay. So this was a brief overview of what the finite element code does. Do you have? I didn't go through in detail, but do you have any question? If not, I'll move on to the next one. So I'll move on to the next phase. So we are done with the training phase.
So make sure whenever.
Then we'll go to the merge phase.
So something sort of to do which has like spaces, because sometimes.
So I didn't run the data definition, I'll run this again, I'll show you the files that are basic. But what merge phase does is, you saw that towards the end, we were saving the data. So it goes into the training data folder. It gets the data that was generated in the first place, in the first
If you want to.
offline stage. One thing that we have to reload the mesh that we used. We don't have to define it, we can just store the defined mesh and we can just call it here. And then
Here I have.
I'll just go to this. So here, this libROM basis generator function gathers all the data here.
He's explaining.
This is the merge file, which is in between the two phases. This offline phase and online phase, this is the merge phase. And the file name is ROM merge.
It has the file.
Are you able to find it? This is the file.
Yeah, you just need to like simply go on it and it was like. So yeah.
This
Don't give any.
gets the
Pieces or something. So,
generated data, which is stored as a basis file,
yeah.
and
You want to like access.
then does the singular value decomposition
In within the library itself.
and stores it in
Folder
situ.
or any folder, clone it, and then give the part of the file.
And finally, in the online phase,
Yeah, you'll be follow the link on each line. Also make sure on the top on the screen, only one thing should run on the. Because only on one.
now
code
we
can
come
access
to
only
the
one thing.
third phase, that's the online phase,
So if you want to like.
where we can test for a, now our reduced order model is already,
Then make sure.
we have the reduced basis that's
And then you
built.
run that command.
Now
This command.
we are going to create the reduced order model here.
Each and every time, but you just need to run this command if you want to like change the file. For example, now if you close this screen and then in order to run this again,
So we again, just like before, in the online phase, we again initialize the parallel environment, we declare the frequency ID, then we specify the arguments for the instance. Remember that here we have to select online.
So.
Because in the previous, when we were doing the merge phase, we had to select merge.
For example.
Here, and in the offline phase, we had to select offline, but here we will select online.
And then it asks for the token.
Then we choose the device again. We did not change the mesh file, we are just importing the same mesh file again. Here we are defining the FE space. And this is where we are importing the basis files that was created during the merge phase. And here, so we read that, we read the basis file. And here we have the reduced basis T. So here we truncate, okay? Just like I defined before, that based on how much variance you want to select in your in the reduced subspace, you want to have in your reduced subspace. Here it's
So in this phase, you are totally independent of what mesh you have, right? You
you do not really need that,
Yeah.
but the thing is, I mean that's not fully true because you have to go back to the full order space, right? So you cannot totally.
So when you need to go back to your full space, you need your mesh, else, I mean, it's not needed here.
Because I mean you don't need the mesh because if you want to visualize your solution, you need the mesh, right?
Yeah.
So here, once we have read and define this reduced basis T, and then we can compute the inverse reduced A. So what is this inverse reduced A? It's basically this Kn inverse. Okay, so Kn is the reduced matrix, stiffness matrix, and here we are going to store that. So we are going to do this U transpose Ku, and we are going to store and then invert it, and we are going to store this is in inverse reduced state. Okay, and then we multiply it with the reduced Qn. So this is the reduced RHS, which is basically Qn. And then we multiply reduced RHS with, this is the reduced salt. So inverse reduced state, multiply it with reduced RHS, stores the value in the reduced salt with this Tn. And then we deconstruct the full order state by multiplying the reduced salt with spatial basis, and this is the XCROM, basically the reconstructed solution. And again, this is happening over multiple cores. We recover the solution. And then this is basically data storage and data visualization. So I think you guys got some, we have provided detailed comments inside the code. When you access it, if you go through it, you should be able to understand. You can always reach out to us if you have any specific questions. So this gives you an overview of what the process is. What we are going to do, we are now going to run this file. So the idea is how many of you are kind of familiar with machine learning, training machine learning models? So as you know that we have a training and the test parameter, we divide the data set into two. So here also we are going to divide the parameter set into two, training and test. And then we are going to evaluate the reduced order model for the test parameters. And the reduced order models are trained based on the training parameters. And then we're going to see, we're going to compare and see how well the reduced order model does. So here I have 20 training parameters, and the training percentage is like 65% training data, 35% test data. And the training data goes in the training data folder. The test data goes in the ROM data folder. And then we also store the solution from the reduced order model in the ROM data folder. So let's run that. So it be installed inside the container. Are you guys able to run this? Any of you here following the steps? You are you able to do it? Yeah. So here I am basically executing this data generation notebook with the training parameters in this. So I think we're going to have approximately 13 training parameters and 7 test parameters.
So how big is your data set? How big is it?
This has 80,000 unknowns, right? So it's a 80,000 cross 80,000. Yeah. Well, no, actually that's not true. You have to subtract off the boundary UFs.
Is it 2D problem?
It's a 2D problem, yes.
You know, 80,000 point. Like you're solving the problem at 80,000 point, right?
For different parameters, we just. Now we can test data. So I'll show you what it generates basically. So it generates these snapshots. So these numbers are not the IDs actually. So this was randomly chosen from 0 to 20. These were the index chosen randomly. And then these are basically text files where you have the solution. Let's see actually the demand. Yeah, we have 80,500, 82,500. These are the bases which will be used in the merge phase. So it's generating the. It's almost done. So now so basically we did 20 full order model solutions. Out of 20, 13 is training data set, 7 is test data set, and for these exact parameter values we are solving the ROM, and we will see what is the speed up that we get and So this is the solution speedup that we get, we almost 4 times with a relative error 10 to the power minus 4. Now, if it were even a larger problem, this speedup would be more evident. So, not bad. Now you have the option to change the mesh as mesh file as well. So let me go back to data generation. Let me see what if you want to bring in your own mesh. So you can have a rectangular mesh. So you can use the G mesh. So on the MFM site, you can so here you can find out the kinds of mesh that MFM supports. So actually, before I go into the mesh, let me show you what the solutions look like. So we have in the ROM data, Paraview online, which is the snapshot or the solutions generated in the online phase. And in Paraview, we have the test data set. So ideally, these should look fairly identical because the error is of the order of 10 to the power minus 4. So we'll choose 14. So I'm gonna use this. I'm gonna use Paraview to visualize this. So you have to generate this. You have to select the PVD file. Okay. This is the data generated by the reduced order model. So we open it, we apply, and you have to go. So in the coloring, you have to choose solution 14, and you have to choose the surface option, which will give you the solution. Okay, so this is the solution generated by the reduced order model. And let's compare it with the solution that was, so this is ROM. Okay. And let's go. So this is the solution that was generated during the test phase. And we'll do the same thing here. So as you can see, there is these two results are virtually identical. There is no difference, at least visibly, because the error is of the order of 10 to the minus 4. Okay. Now, as I was saying, we can use different other mesh files as well. Let's look at one interesting mesh file that was given to me by Professor Ragusa. I hope this will. So I'm going to run the data. You can also run this data generation file directly. You don't always have to use this full process. So you can generate a solution for a particular parameter value, but just by running this as well. So this ran. So for this, the ID is 0. Because the default ID for this notebook is 0. So I'll look into the solution generated. This actually generated the data inside the training data, so. So this is basically the mesh file. Let me do one thing. Let me regenerate this, but let me change the frequency of the flux density here. Let me make the frequency lower. Sorry. Then it will be. This. Because the mesh size is significantly bigger than the star mesh size, so that there was this issue. The frequency of the was comparable to the mesh dimension. So basically, you can have your own mesh and solve a heat conduction problem on that, and for that matter, any kind of problem. So I think that concludes our session 3. And then we'll again take a short break and we'll come back with non-intrusive starter modeling. Thanks for bearing with me. Okay, let's resume. And we are at the last session. Almost there. Thanks for bearing with me for 3 hours almost. So, as mentioned earlier, this session is totally different from the previous session. Here, we are going to focus on non-intrusive modeling of dynamical systems. Specifically, we're going to look at dynamic mode decomposition. So previously we looked at the intrusive section. Now we're going to look at the non-intrusive one. So here the premise is that we have data from the simulation of some model, and it doesn't have to be simulation. We can just have data that which the time series data, and we want to come up with a model that can describe the behavior of the data, and we can use that to perhaps predict how the data is gonna look like at a future time. So when we have the choice to come up with a model from data, our default inclination is towards deriving a linear model, right? Because it's easy to analyze, predict, and we have a lot of tools in our arsenal to analyze linear systems. So here, for example, this is an equation of a linear model where AC is the continuous time operator that governs the system's dynamics. But many a times our data is not continuous. It's discrete and collected at specific time intervals. So it's more practical to find the discrete equivalent. Here, as shown here, this operator A maps the state at time t equals to tk to at time t equals to delta t. So basically one time point to the next. So this is, now can we estimate A just from the data? That's basically the question we are trying to answer here. So we want to identify the best fit operator, right? That advances our state from one time to the next. So say we have T, say T is a matrix where we have collected the solution snapshots at successive time steps from a source, from a model, from probably later, whatever. And we build another matrix T prime that's almost the same matrix, but it just advanced one step in the future. So T prime is shifted one delta T in the future. So in T we start with the solution at or the initial condition, and then we advance. So the second column represents T1 and the kth column represents Tk. K plus 1 column represents Tk, but here we have the first column is T1, then T2, and so on. Now we want to find out the mapping A that best maps T into T prime. Okay. Now what happens when we say that we are able to do this? So if we have this A, we can then from this equation we can write that we can use A to come from the initial condition to Tk, and basically then we have a relationship between Tk plus delta T and the solution at the initial time. All we have to do is to evaluate this A to the power k plus 1. If we further do an eigen decomposition of A, we are left with phi lambda to the power k plus 1 and p transpose, where phi is the eigenvector of A and lambda is basically eigenvalue of A. Now this is diagonal, and by no means these are real numbers. These matrices can be complex and will be complex most of the times. But it's very easy to calculate this because all you have to do, once you have calculated phi, all you have to do if you want to advance to kth time step, you just have to take the power k plus 1 for lambda, and lambda is a diagonal matrix, so it's very cheap. Yes.
So has delta T be uniform? How can I say that? Does delta T have to be uniform for all the snapshot? Let's say that between the first and second snapshot, delta T is something, and should it be the uniform for?
So the framework that I'm presenting here, for that it is, but in general, DMD doesn't depend, it doesn't have to be that. And here, so this is the size for phi and lambda, which is r to the power n plus n. So just keep this in mind. And now let's forget this part. Let's just focus on this for now. How can we? What is the easiest way to find out A? Can anybody guess? Do you want to try? Yes. So we're assuming uniform sampling in time. So what we can show that the best operator who maps T into T hat is actually the least square. So we can find out A just by doing the least square of the data matrix. But the catch is that the A obtained in this way is prohibitively large, right? So it's n cross n, and if n is very large, then you are against kind of stuck. You obviously have a model, but it's very difficult to simulate that model, right? And finding out the eigenvalues and eigenvectors will be a challenge. So what DMD does, it derives the leading eigen decomposition of A. So instead of finding A, we find out the leading eigenvalues and eigenvectors of A using DMD. So we don't actually have to calculate A ever. Okay. So what is the idea is that DMD, instead of deriving A, focuses on a projection of A tilde onto a low dimensional subspace derived from the snapshot matrix T, assuming that the dynamics is embedded in that subspace. So it follows the same idea. So in the previous few slides, what I was talking about is that you have the data set and you can derive a reduced subspace because the dynamics is embedded in that subspace. So what we can do, instead of deriving A in the full order space, because the dynamics is embedded in a reduced subspace, let's focus on a reduced representation of A in that subspace. Okay, that's kind of the basic idea. And then, so say this T is the data matrix, and we truncate up to n modes to get a reduced representation of T, and then we find out this U tilde. And we now have A tilde, which is U transpose A U tilde. And remember, we don't have A, okay? We don't have A, but we know that theoretically A is T prime times T pseudo inverse, and then we can replace the expression of T pseudo inverse based on this expression, and we get this. Okay. We have V tilde, we have sigma tilde, and we have U tilde, and we have this T prime. Okay, so we actually didn't do a pseudo inverse. And in this way, we are able to find out what A tilde is. But what was the objective? Was to go from T at time T0 to Tk plus delta T. And previously, I showed an expression where you didn't have these tildes on phi or lambda, right? So what it can be, so we can prove that once A tilde is formulated in this way, because it's very small, we can find out the eigenvalues and the eigenvectors of A tilde much easier, very easily, because it's a small matrix. Okay. Now we can use the eigenvalues and the eigenvectors of A tilde to find out phi tilde and lambda tilde. Yes.
P tilde is the matrix of eigenvectors, right?
A tilde is the approximation of A. Phi is the, yes,
Eigenvector matrix.
is a reduced representation of phi. Yes. Phi is n cross small n, and lambda tilde is small n cross n. So it can be theoretically proved that lambda tilde, which is the eigenvalues of A tilde, is a subset of lambda. It can be theoretically shown. And one can obtain phi tilde, the first few columns of phi tilde, the leading eigenvectors of phi, which we are writing as phi tilde, can be found out using this expression. Okay, where we utilize the eigenvectors of A tilde. So we are never actually calculating the A. We are not calculating the eigenvectors of A or eigenvalues of A. Rather, we are using this A tilde to approximate phi tilde and lambda tilde. Okay. Once that's done, we can basically, so I'll go back. Instead of this expression, we can replace it with these approximations, and it gives us a model that advances the state at the initial time to a state when we want to have it at tk plus delta t for any case. So you basically don't have to use an integrator as well. You just directly go from initial condition to the kth time step.
But it should be some kind of scope, right? So probably cannot estimate, for instance, after the, I don't know, 1 year or something, right? It cannot estimate that state. So it should be some kind of threshold value for making a temporal extrapolation, right?
Yeah, I mean, that's true. It depends on if the underlying system is extremely nonlinear, for example, it's not gonna work. You can find out the best linear approximation of that nonlinear operator, but that's about it. It cannot. It depends on the actual process. There is something called window DMD where you can probably chunk. You can chunk the data into different windows and have different DMD models for that.
But at least we can make some kind of temporal extrapolation, right? We can estimate some time, not probably going to be huge. But let's say
yes,
the 1 second or something
Right.
after 1 second, what happens?
So if you remember that I showed some of the examples when I was introducing pylibROM, where I just quickly go back. So where you remember the laser tracing problem for additive manufacturing and the beginning?
That's right.
Yeah, this one. So all of these are basically done using DMD. And we had fascinating speed up and pretty good accuracy. So it's pretty powerful. Every method has its shortcoming. So summary, it's useful for large scale time dependent problems. It's used when a high dimensional model is not available, and it derives a purely data driven linear surrogates, and it's applicable for both nonlinear and linear problems, but you have to use it wisely. If the underlying, again, as I was saying, if the underlying method is too nonlinear, then probably it will not work that great. And so let's look at DMD with pylibROM. So here, previously we had a steady state problem. Here we have a transient heat conduction problem, and the finite element formulation leads to an ODE instead of an algebraic equation, and it's a stiff ODE, so we have to use implicit schemes to solve this problem. So let's look at a very specific problem. So again, we use a similar problem as before. We have this transient heat conduction PDE. Here K is assumed to be 1, and we assume that the flux is 0 at the boundary. In the previous case, we had Dirichlet boundary condition where the temperature was basically 0 at the boundary. Here we have the flux, heat flux to be 0. At the boundaries, it's an adiabatic case. And so we have two files in session 4. One file basically uses finite element to generate the data for this simulation. It does all the 4D simulation and everything. And then the other code, as Pravija will show you soon, that the other code is basically collects that data generated by the FEM code and implements DMD to find a linear model. And this basically is the initial temperature profile. Okay, so we have the temperature value is 2 within a circle of radius 0.5, centering at the origin. And if just after beyond that circular domain, the temperature of the entire domain is 1. Okay, so we want to see how this temperature profile evolves in time. So what I am not going to go into the details of the finite element coding for this. So I'll quickly stop sharing once. Every time I show a code, we have to do this. Apologies for the inconvenience. Changes. So let's come to session 4. So we have the heat conduction data generation code here. This is basically a finite elements code. So the plan is not to go in into the details of this code. Basically, the data can be generated from finite element method, finite difference method, finite volume method. It doesn't really matter. Once we have the data, we can use the DMD to generate a linear model that that can approximate the behavior of the data. So you can go through this on your own. We have commented on this heavily so that you can understand steps that's going on. And so all it does is basically generates the time series data for that particular problem that I showed. What we are gonna, once she is done explaining the DMD, she's gonna show the results from this finite element code and the results obtained using DMD and compare it and show how the two results look like. Okay, so Pravija, you can take over. But let me just run this file so that the data is generated. Which will be used by this ROM DMD node. So it's basically solving the ODE. I think it goes 3.5 seconds. Right? So we are simulating the full order model right now using finite element. Okay, so it took around 37 seconds to generate the data. Now, I think, so let's see how.
So yeah, now that we have generated the data, now we need to just train the DMD model with the generated data. So it's not necessary to create a mesh file again, but in order for the visualization purposes, I'm generating a mesh file here. I'm just creating a mesh file. And then now, yeah, here comes the DMD part. We need to initialize the time variables and we need to record the timestamps. And here I'm initializing the DMD training timer and prediction timer with stopwatch. And like he said, we have stored the data in URA.npy file. So now I'm going to load the data again into the URA array, and yeah, and then we are going to iterate through the URA and the DMD object. We are going to initialize the DMD object. The DMD object takes the data for each time step, and then it aggregates the data and internally it stores in a snapshot matrix. Yeah, this is a snapshot matrix that internally that DMD is going to compute by taking the sample at each time step from the data that we have generated from the full order model. So once that's done, now we need to before doing all the steps, we need to give we need to set the R dimension or energy fraction. I mean this basically says that for how many modes do we need to compute the DMD for. So if we set both of them with some values, then the energy fraction will be ignored and only the R dimension will be taken, and we'll train the DMD with the number of modes that we specify. And if we here in this example, we are going to give the energy fraction as 0.999. So internally the DMD algorithm will compute at how many modes the model can predict the data accurately for all the time steps. Based on that, it internally calculates the reduced dimension modes, and then it trains the model on that. It trains the data and it generates a model. And once training has completed, now we are going to predict. Now once we have trained the DMD model, we can predict it for at any time step. So here the k can be any value. So here in our example, we are predicting it at t final, and the result is stored in result Q array, and we are going to compare the relative error between the original solution and the solution that has been generated by DMD. And as you can see, the relative error of DMD at t final is 0.0014, which is very, very low. And also the time taken for predicting at that particular time step is 0.0118, which is very low as compared to the full order model. The full order model, it nearly took 3.77. So
37 seconds.
yeah, 37 seconds. So this demonstrates us that once we have trained the DMD model, we can predict for any time step, and it pretty much gives the accurate results. So here this is the visualization part. I'm creating a paraview object, and then I'm calculating the DMD model. I mean, I'm predicting for every time step, and I'm storing it in the result queue, and then I'm giving it to the paraview object, and I will run this once and we can see the results.
We can run this parallel, right?
Yeah, we can run this parallel. All of the libROM codes are parallelized, so you can run it in.
Do they scale?
What?
Do they scale when you increase the processor node number? Have you checked that, for instance?
Yeah,
They are scaled.
it worked. And also, if you want to use our TAMO HPRC also has pylibROM installed, so you can go and check there. You just need to go to the interactive sessions in HPRC, and then there you can select, we'll share a mail, the steps that we need to follow in order to like set up pylibROM environment in HPRC.
So this is the simulation for the original high-dimensional model that we obtained from finite element analysis. So as you may remember, this was what the initial temperature profile was. And then if we play this, this is a linear conduction problem. It's not that interesting, it's just because it's a diffusion and there's a diffusion term, it just diffuses the concentrated temperature throughout the domain. So that's what we obtained from the full order model. And now let's see how the EMD model performs.
The PD here is linear.
PD is a linear conduction problem. It starts similarly. So this concludes the demonstration, code demonstration part. So here I have a few online resources that once you have this PPT, you can use these. This will give you more some in-depth understanding of reduced order modeling. And I have also noted down the MFEM, link to the MFEM library, because some of these examples heavily rely upon MFEM. So it may be a little bit confusing. So, but they have a very nice repository here. We have, where there's a lot of documentation. So this concludes the, at least from our side, we don't have any other material to share. If you have any questions, now we can